Hi everyone, this is K. from ECD section. So today I want to discuss about the Laplace transform of impulsive function, which is the topic in Laplace transformation. So while entering into the topic, what is Laplace transform of impulsive function? It is a function. It is a function which exists only at t equals 0 and is 0. Elsewhere, the function is also called as a delta function. If the value of t equals 0 in this function, then it is called as a Laplace transform of impulsive function. Else, if not, it is called as a delta function. The unit impulsive function denoted as a function delta of t, where the function in terms of t. The amplitude of the impulsive function is infinitely large at t equals 0, but for unit impulsive function the area under the curve is equal to 1. The unit impulsive function is shown in this graph. So when the value t equals 0, the impulsive function is larger, and in the function delta of t is not equal to 0, and we get the area equal to 1. So it is a graph denote the delta of t function, which the area under the curve is equal to 1. So it indicates the area under the pulse. Mathematically, it is represented as delta of t equals 0, where t not equal to 0 and area under the pulse is unity. That is integration of limits minus infinity to infinity of delta of t into dt equal to 1. So the area under the curve or pulse, we get the equal to unity. The concept of unit impulsive function can be further simplified by the following discussion. So let us see the detail. Consider a rectangular pulse of unit area having width a1 equal to width and amplitude. Consider a rectangular pulse of unit area having width t1 and amplitude is 1 by t. Here width is t1 and amplitude is 1 by t1. Then area equal to width into amplitude. So it is equal to t1 into 1 by t1, where we know as area is unity. And if now width is decreased from t1 to t2, then to have unit area of the pulse, its amplitude must increase from 1 by t1 to 1 by 2. So if we have to maintain the area under the impulsive is 1, we have to decrease the width. If the width is changes to or decrease to t2, then automatically amplitude of the function increases to 1 by t2. So now we get the area of impulsive function equal a2 equal t2 into 1 by t2 equal to 1, where t2 is less than t1. If the width is further decreased to t3, then we have to unit area of pulse amplitude will further increase to 1 by 3. So if the width continuously decreasing by some term, then amplitude of the function will also increase. So we get the third area equal t3 into 1 by t3 equal to unity, and where t3 less than t2 less than t1. So in the limiting case, now if the width tends to 0, then the amplitude of the pulse tends to infinity. So to get the unity area, such a function that is impulsive pulse with infinity amplitude and 0 width having unit area under the pulse is called unit impulsive function or delta function. So when we are calculating the area of the pulse, where the width is equal to 0 and function means amplitude of the function tends to infinity, it is called as a impulsive function or unity impulsive function or delta function. So here you can see the graph defining the area of the impulses where the area equal to unit. So from the figure we can write that if f of t is the pulse with t and the unit impulsive function is 0, so then delta of t equal limit t tends to 0 and f of t, where delta of t equal to area equal limit tends to 0 t into 1 by t equal to 1. Here f of t equal t into 1 by t, and the area is unit. The unit impulsive function can also be obtained using step functions. The unit impulsive function is the limitive case of rectangular pulse. A rectangular pulse can be obtained by subtraction of two step functions as shown below. So here you can see the rectangular unit impulsive function. A graph defines the area of the rectangular pulse. So hence the rectangular pulse can be expressed as f of t equal to u of t minus u of t minus t, where u of t is a starting and u of t minus t is a ending point of the width or length. This is a pulse of width t, and unit impulsive function having the unit area under the pulse can be written as delta of t equal limit t tends to 0 1 by t into u of t minus t, where u of t minus t is the width of rectangular function. So we are going to discuss about another function called delayed unit impulsive function. It is similar to the delayed step or ramp. There exists a delayed unit impulsive function. So here you can see the graph related to the delayed unit impulsive function. It has unit area but existing at a t a equal to a as shown. It is denoted as f of t equal to delta of t minus a. So in this, t changes to a. In normal impulsive function, t equal 0, here t equal to a, so we get f of t equal delta of t minus a. So here are some important properties of the impulsive function, where there are two important properties of impulsive function. First one is shifting property. Mathematically, this property is expressed by the integral, where like integration of f of t into delta of t minus t capital T into dt, where limits are minus infinity to positive infinity, which is equal to f of t. Here delta of t minus t delayed impulsive function mathematically. So, and another property is replication property. This property is mathematically given by integration of f of t into delta of t minus rho into delta of rho equal to f of t, where limits are minus infinity to positive infinity. This property tells that convolution of any function with an impulsive function result into original function. So we get the original function from this function by using replication property. So I think you have understood about the unit impulsive function, and delayed impulsive function. Thank you.